Hello students. So today let us study another interesting topic which is in chapter 2, class 11, right? That is structure of atom. Inside structure of atom, we have this topic that is Bohr's model of an atom. Okay, so let us understand what is Bohr's model of an atom. Okay, so basically this model was proposed by Niels Bohr in the year 1913, and he explained basically the structure of hydrogen atom, and he also said that this model of an atom that we're going to study today, it works only for atoms that have like only one electron. For example, hydrogen, we know it has one electron. Helium plus, right? Helium, we know that the atomic number is 2, but helium plus means one electron is lost. So now the number of electrons are how many? There is only one electron, right? Lithium has how many electrons? Can you all tell me? Yes, lithium has 3 electrons. So if it loses one electron, it becomes lithium 2 plus, right? Sorry, 2 electrons. Then only one electron is left, right? Okay. And he applied, quantum theory to the atomic structure. So this is an introduction, and all of this we are going to study today. Let us start. So basically, let us understand the main postulates that he gave to us. Okay. So he said that electron revolve in fixed circular orbits around the nucleus. So we know that, we have nucleus, and inside the nucleus there are protons and neutrons, and we have like fixed orbits like this. Okay. So we have fixed orbits. So electrons, they revolved around these fixed orbits, right, around the nucleus. And each orbit has a fixed energy. Like, for example, if I talk about the first orbit, so we represent it by n, right? N is equal to 1. So the orbit, that is the first orbit, it would have like a fixed energy state. It would have a fixed energy. Okay, then the second shell, that is n is equal to 2, it would also have a fixed energy. So it's not like that electrons can go anywhere. They go into these shells, and these shells have like a fixed energy. Since they have fixed energy, we call them stationary states or like energy levels. So like first shell would have certain fixed energy, second shell would have certain fixed energy. Also, when electrons are revolving around these orbits, no energy is lost. Basically, these shells are the ones who have energy, right? And electrons does not have any energy. These shells have energy. Okay, and these orbits, they are termed as n. N is the principal quantum number that we are going to study in, the next topic, that is quantum numbers. N is equal to 1, 2, 3. Basically, these are the orbits, right? As you must have studied in class 9, that the first orbit, we even call it K. The second, we call it L. The third, we call it M, right? Okay, so let us understand. So Bohr, he talked about energy quantization. What is the meaning of the word quantization? Quantization means when something is fixed. So basically, he said that, every orbit has like a fixed energy, right? For example, okay, if I draw this, I have first shell, I have second shell. Okay, so he said that orbits, where, okay, so allowed orbits are those where angular momentum is quantized. What is angular momentum? We already know that angular momentum is equal to mvr, which is n into h by 2 pi. So he said that the n value, right, for particular shell, it should be a whole number. Only like, so this is how we can calculate the energy, right? So n should be a whole number, 1, 2, 3. It cannot be in decimal form. It should be a whole number, right? And n here is the principal quantum number, that is the shell. That is the first shell, n is equal to 2. For second shell, n is equal to 2, right? For third shell, n is equal to 3, right? And for these particular shell, only certain energy values are allowed. Like first shell has a fixed energy, second shell has a fixed energy, right? And electron can enter those shell. Like for example, if you create, for example, if teacher creates spaces, like there is a first row, then there is some space, then there is second row, then there is some space, then there is third row. So children can only sit in the rows, like first row, second row, third row. It's not like children can sit in between. So that is why, these orbitals, these energy levels, they are quantized, right? So orbits, allowed orbits are those where the angular momentum is quantized. Quantized means it should have like a fixed energy. The value of n should be a whole number. It should not be a decimal. Okay. Now, what else did Bohr tell us? That electrons can jump to a higher orbit by absorbing energy. Let us understand. For example, this is uh, any atom, let us consider. This is the nucleus, okay. So let us consider this is the first shell and there is an electron here, okay. So, okay, now electron, when it absorbs energy E, right? So basically it absorbs energy and it can jump to a higher orbit. Let's say n is equal to 3, right? Okay, so it jumps here. So now when it is jumping up, it has higher energy, right? It has higher energy because it has absorbed energy. But you know, the electron, it is not stable at higher energy. See, in chemistry, throughout chemistry, high energy means low stability, okay? And low energy, that means less energy. If the energy is less, so I'll just write it here. Less energy means more stability. It means higher stability. So the less energy the electron has, the more stable it is, right? So when electron gains energy, it gets excited. So now it has greater energy. It is in an excited state, but it is not stable. So the electron cannot stay at the third shell for a very long period of time. What happens after some time? It emits energy and falls back to its ground state, that is its original energy shell, right? Okay. And during this period, it emits certain energy, right? This energy difference we can find out by delta E is equal to E2 minus E1. And we all know that energy is equal to H into nu, right? So we can find out delta E is equal to H into nu. So, you know, through this, he explained the hydrogen emission spectrum. Now, hydrogen emission spectrum is a very big topic. If you want to learn it in detail, you know, you can contact me through my Urban Pro profile, right? Also, when the electron comes back to the first shell, now it is near the nucleus. And we all know that the nucleus has a positive charge and positive and negative are attracted to each other. So because of that, also the electron is much more stable in the first shell, right? It has less energy and it is more stable. So always remember this, if the energy is high, the stability is very, very less. If the energy is low, the stability is more. Okay. So what is the significance of this Bohr's model of an atom? He explained the stability of atoms. He explained the spectral lines. Now, spectral lines like Lyman, Balmer, Paschen, bracket, P fund. So it's like a another concept. We'll study it when we get in touch, right? Through the urban profile. Okay. And this was the first model which used the quantization concept, the concept of quantization. That means that energy is there in fixed quantities, right? There is a fixed quantity. That is the meaning of the word quantization. Okay. Now, there are certain limitations for this. It does not work for multi-electron atoms. As I told you in the very first slide, it works only for atoms which have only one electron, right? And it could not explain the Zeeman effect, the Stark effect, the Heisenberg's uncertainty principle, and even the de Broglie hypothesis. Now, if you want to learn what is Zeeman effect, what is Stark effect, what is the de Broglie hypothesis, what is Heisenberg's uncertainty principle in detail, again, we can connect together because it is like a huge topic. Okay. Now I have some questions for you. If you would have understood whatever I taught you, you would be able to answer these questions. Bohr's model applies to, what do you think? It applies to all atoms, one electron atoms, or molecules, right? Just think and tell me, okay? Electrons lose energy. Do electrons lose energy while revolving? Yes or no? Next question. Energy is emitted when electrons. So when is energy emitted? Emission means released. When is it emitted? When they move to higher orbit or fall to lower orbit? I think these questions are very easy. And if you would have heard me clearly, you would have, known the answers. So here I have answers. Bohr's model, it applies to only one electron atoms, as I told you, hydrogen, helium plus, lithium 2 plus, right? Next is electrons lose energy while revolving. So I clearly told you electrons do not lose energy and they do not even gain energy, right? So the answer is no. Next, question number 3. Energy is emitted when electrons. So when is energy emitted? So I told you when the electrons, when they fall from the higher orbit to a lower orbit, that is when the energy is emitted, right? That's the correct answer. The correct answer is option B here for question number 3. Actually, energy is absorbed when they move to higher orbit. Energy is absorbed. When they're coming down, energy is emitted out, right? So here are the answers. You can check the answers. I hope in continuation after Bohr's model of an atom. So today we are going to study about quantum numbers. So you might be thinking, what are these quantum numbers? First of all, it is a very easy and a very interesting topic. Okay, like how, we tell our address to someone. For example, I live in Banaras and this is the street, and, after street, this is the house number, right? So, that's just an example, right? Just telling everyone your address. First, you will tell your country, then you will tell your state, then you will tell your city, you will tell your street, right? So, quantum numbers, basically, these are four set of numbers that describe the address of an electron. Where is the electron present inside an atom? So, there are four quantum numbers. This is a very easy and interesting topic. First one is the principal quantum number. Okay, we are going to study it in detail. Next is angular quantum number, which is represented by small l, and magnetic quantum number, which is represented by m. We have spin quantum number represented by small s. Okay, let us start. First, that is the principal quantum number. It represents the shell. Okay, it represents a shell in which the electron is present. Like, in 11th class, you have studied about K, L, M, N shell, right? So, N is equal to 1 means we are in the K shell, right? If N is equal to 2 means we are in the L shell. N is equal to 3 means we are in the third shell. N is equal to 4 means we are in the, fourth shell, which is the N shell. Okay, it represents a shell number. For example, I say n is equal to 2. So this is telling me the shell number that my electron is in the second shell. Okay, and it also gives information about the size of the shell and the energy. So the greater the n, the more the size, as you can see here, and also the energy increases, because I told you the closer is the electron near to the nucleus, the less is its energy, because it is more stable. If an electron is near the nucleus, so basically nucleus has a positive charge and electron has a negative charge. So it can stabilize because of the force of attraction between them. So farther the electron goes away, the energy increases, right? For example, check the radius, right? N is equal to 2. The size is more, right? N is equal to 3. The size is even more. So as the principal quantum number keeps on increasing, the energy also increases and the size also increases. I hope you understood about the principal quantum number. Next is the azimuthal quantum number. Now it gives us the information about the number of subshell and also the shape of the orbital. Number of subshell and shape. Okay, what do I mean by the shape and number of subshell? So you must have known about the S, P, D, and F subshell in chapter 4, that is chemical bonding. Okay. So S subshell is what? It is spherical in shape. P is a dumbbell shape. D is a double dumbbell shape, right? So it tells us the number of subshell. For example, if L is equal to 0, that means I am referring to a S subshell, right? If L is equal to 1, that means I am referring to P subshell. If L is equal to 2, I am referring to D. If L is equal to 3, I am referring to F, right? Okay, now for any principal quantum number, how do you calculate the number of subshells, right? So how do we calculate it? For example, I have n is equal to 1, right? So n is equal to 1. Just a minute. Yes, so for n is equal to 1, my principal quantum number n is equal to 1. How do I calculate the azimuthal quantum number? So azimuthal quantum number is anywhere between 0 to n minus 1, right? So here n is 1, okay? So n is 1 and L is 0. So 0 to n minus 1 will be what? It will be 0 only, right? Because 1 minus 1 is 0. So I have just one shell, that is 1s, because I told you L is equal to 0 represents S subshell. Okay. If I have n is equal to 2, so the the azimuthal quantum number ranges from 0 to n minus 1. So n minus 1 is what? 2 minus 1, right? That means 0 to 1. That means 0, comma 1. And I told you that L is equal to 2 is, L is equal to 1 is P subshell. So we have 2s and 2p. Why is 2? Why are we calling it 2s and 2p? Because now this is in the second shell. This s orbital is present in the second shell, so I'm calling it 2s. And this p orbital is also present in the second shell, so I'm calling it 2p, right? Okay. Next, if I have n is equal to 3, right? So my range will be from 0 to n minus 1. Now n minus 1, 3 minus 1 is 2. So I have 0, 1, 2. So rest, I think you can calculate it yourself. Azimuthal quantum number, that is also known as angular quantum number. Just now we studied about it, right? Okay. So in azimuthal quantum number, as I already told you, that L, 0 is S, 1 is P, 2 is D, 3 is F. And these are the shapes of the particular orbital as the azimuthal quantum number tells us about the shape and the number of subshell. So for S, the shape is spherical. For P, it is dumbbell. You know, this is looking like a dumbbell. And for D, it is a double dumbbell shape. Okay, next, the third quantum number is the magnetic quantum number. Basically, it tells us about the orientation of orbitals. First, let us understand, okay, about the orientation. For example, if I have p orbital, so you know, p orbital is a dumbbell shape. So the orientation of p can be like this. It can also be like this, and it can also be like this. As you all know that in 3D, we have x axis, y axis, and z axis. If it is along x-axis, we call it px. If it is along z-axis, we call it pz. If it is along y-axis, we call it py. So it gives us orientation of orbitals, right? Okay. So for example, I have p orbital, but what about its orientation? It can be py, it can be px, it can be pz, right? And it also tells us about the number of orbitals. So for let us say for p, I told you the L value is 1. So now this formula 2L plus 1 would tell me the total values. Okay, so 2 into 1 plus 1. That means I have 3 orientations. And what are these 3 orientations? It will be minus L to plus L. That will be minus 1 to plus 1. Okay, so minus 1 to plus 1 has what? Minus 1, 0 and plus 1. So number of orbitals are 3, right? Okay, well, let's say S. Okay, we know that for S subshell, L is equal to 0. So we put 0 here. So total value will become what? Let us understand. It will become 2 into 0 plus 1. Okay, that is 1 only, right? So it has this one orbital and it ranges from minus L to plus L, right? So minus L to plus L is what? Let us understand. So it is 0, right? 0 to, okay, so 0 will remain 0. So number of orbital is just 1. Similarly, you can calculate for D, you can calculate for F. Okay, so D orbital, it has, 5 different orientations. F orbitals, it has 7, right? Okay, so this is how we calculate the magnetic quantum number, that is from minus L to plus L. Now let us understand the final quantum number, that is the spin quantum number. So spin quantum number is the last quantum number which tells us about the spin of an electron, whether it is rotating clockwise or whether it is rotating anti-clockwise, right? Okay. If the spin is plus half, that means it is rotating clockwise. If the spin is minus half, that means it is rotating anti-clockwise. So that is what spin quantum number tells us about, right? Because no two electron in a particular orbital can have the same spin. They should always have an opposite spin, right? So let us just recall whatever we studied. We studied about the principal quantum number, that is n is equal to 1. Like that is represented by n. If it is n is equal to 1, that means we're talking about the shell, right? We're talking about the energy level, right? Okay, then we talked about the azimuthal quantum number represented by L. That tells us about the shape, okay? Then we talked about the magnetic quantum number, right? Which tells us that is ML. That tells us about the orientation of the orbitals. Then we have spin quantum number MS, which tells us about the spin of the electron, which is present in that orbital. So basically, we are finding out the address of the electron. First, we go into the shell, principal quantum number, then shape. Okay, after shell, now it is in which subshell, right? Like S, P, D, F. If L is equal to 0, okay. Suppose if n is equal to 1 and L is equal to 0, what does it mean? That my electron, it goes into the first shell. In the first shell also, it goes into the S orbital, right? Okay, then the magnetic quantum number ML, right? So for L is equal to 0, magnetic quantum number is 0 only, right? That means it is in 1s orbital. Okay, what is its spin? Is it plus half or is it minus half, right? Because it can be plus half or it can be minus half, and no two electron in a particular orbital can have the same spin, right? So this is about the quantum numbers, which I tried to complete in a very short span of time. But if you want to learn it in detail, we can connect to the Urban Pro profile, right?